Hello and welcome back to the alphabet of astronomy. Today is brought to you by the letter S, and S is for spectra. So I'm really excited about this one because spectra come up a lot in astronomy, and so I'm really excited to really dig into this and give you an idea of just what we're talking about when we're talking about something's spectrum. So in astronomy, a spectrum just measures the intensity of light at different energies of light. That's it. Now there's a few different ways that you can quantify the energy of the light. So this is going to be the x-axis of a spectrum. So you can just use energy of the photon. But we also know that the energy of a photon is related to both its wavelength and its frequency. So you might also see frequency or wavelength as the x-axis. And there's something called wavenumber that you will sometimes see as well. Now wavenumber is similar to a frequency. So for light, it travels at c, the speed of light, and you can relate the wavelength and the frequency by taking c divided by the wavelength to get the frequency. And this will give you a unit that's per time. However, you can also count the number of cycles per length, and so this is just 1 divided by the wavelength. And so instead of having a per time like a frequency, the unit is actually going to be a per distance, and so it's cycles per distance, but it only varies from the frequency by a constant factor. Now for all of these different quantities, there are somewhat typical units that we tend to use. So for example, for energy, the unit that you're probably most likely to see is electron volts, ranging from maybe kilo-electron volts to giga-electron volts. For wavelength, you'll probably see nanometers, which is 10 to the negative 9 times a meter, or angstroms, which is 10 to the negative 10 times a meter. The typical units for frequency are the hertz, which is a per second, and you'll see this ranging from kilohertz to gigahertz. And for wave number, the most typical unit is an inverse centimeter, or a per centimeter. Now remember, while these are different quantities, they can all be easily converted between one another, and they're all describing the same thing, which is basically just the energy of the photon. And different fields will have different kind of common practices about what they tend to use for the x-axis of the spectra. Okay, so that's the x-axis of a spectra. What about the y-axis? So the y-axis is usually going to be some measure of intensity. Now this can vary quite a lot in what particular unit is going to be used. It could be something as simple as counts, that is the number of photons at any given energy level, or it could be something as complicated as a unit called a Jansky, which is often used in radio astronomy and is a watt per meter squared per hertz, I believe. So basically, just keep in mind that what the y-axis showing is kind of the relative intensity or strength of the light at any of the given energies from the x-axis. Okay, so that is kind of the basic breakdown of what exactly you're looking at when you're looking at a spectrum. And it might sound kind of confusing, but actually you've probably seen many spectra before in your life, because if you've ever seen a rainbow, that is just a visible light spectrum of sunlight. In that case, the intensity would just be how bright each color appeared to you. So we can actually use that kind of rainbow breakdown for any spectra, and it might look something like this, and then it might be a little bit easier to visualize. However, astronomers typically work with plots for spectra, so it's going to show the actual quantification of that intensity with that y-axis. Now the reason that spectra exist basically is because of the interactions between light and matter, in this case matter being typically electrons or other very small charged particles. Now we talked about this in a bit of detail regarding opacity, and indeed these are very closely related concepts. Now I'm not going to dive into these actual interactions too much in today's video, but just know that there are underlying quantum physics that can basically explain the reasons that we do see spectra like this. So there are 3 main types of spectra that we use in astronomy: continuum, absorption, and emission. So a continuum spectrum is something that's coming from a dense object and that it's relatively uniform over different wavelengths. That is, it would make a smooth line in one of these spectral plots. Now probably the most common type of continuum spectra is the black body spectrum. So this is the thermal radiation that's emitted by a body that is a perfectly absorbing body. That is, it's black. It doesn't reflect any light. All of the light that's coming from it is being emitted from itself, basically based on its temperature. The shape of a black body spectrum is defined by something called Planck's law, and it is very closely related with the temperature of the object. Now, while astronomical bodies aren't perfect black bodies, it's a very good approximation for many of them. For example, we typically use black body spectra to describe stars. So this is an example of a perfect black body spectrum at the same temperature of the sun, as described by Planck's law, and then also plotted is the sun's actual spectra. And you can see that it follows pretty closely, but not exactly. We'll get to that later. But while they're very common, black body spectra are not the only kind of continuum spectrum. Other sources of continuum spectra include bremsstrahlung, synchrotron radiation, and Compton scattering. Okay, so the next kind of spectra is an absorption spectrum. So this is a spectrum where light at given discrete wavelengths, so not a continuous smooth line, but at very specific wavelengths, is absorbed from some background continuum spectrum. So again, looking at this comparison of the sun's actual spectra to a perfect blackbody, we can see that a lot of the departures occur at very specific wavelengths where there's just big dips beneath what would be a typical blackbody spectrum. And this is the absorption spectra of the sun. Now this goes back to those quantum interactions that I was talking about. So basically, light at a certain energy can interact with certain particles in a given way, and this will basically remove those photons from the background continuum spectrum. This absorption occurs in some sort of cooler and sparse medium that's in between the blackbody source and the observer. So something like a nebula might have an absorption spectrum because it is absorbing light from behind it, and we can maybe see, for example, what the nebula is made of because we know those given wavelengths are correlated with certain elements or atoms. But wait, I said that the sun's spectra has a lot of absorption lines in it, and there's definitely not a nebula in between us and the sun, so where is that absorption spectrum coming from? Well, this is actually coming from the atmosphere of the sun, and that counts as a cooler and sparser medium through which the sun's blackbody radiation from its core is passing. And so these absorption lines in the sun spectra actually tell us about the composition of the sun itself. And even though when we typically see a rainbow by eye, we can't actually tell that there are these missing absorption lines, if we zoom in using special instruments that help us actually see higher resolution in wavelength, you can clearly see these kind of black spaces where there's just no light coming at a given wavelength. So any given star has what's called a spectral class, for a sun that's a G, and this is basically a division between stars, a way of breaking them up based on their spectra. So nowadays there are 7 main categories in this spectral type classification: O, B, A, F, G, K, M. And these actually correspond with the mass and temperature of the individual stars. So O stars are the hottest and M stars are the coldest. Now, if we look at the spectra, an example spectra from different stars of each of these spectral types, you can see that the spectra vary quite a lot as you move from O to M. Now, one reason for this is, like I said, the temperature. So O stars are very hot, M stars are not, at least for stars. And the blackbody radiation depends on that temperature. So as the temperature gets lower, the blackbody peak moves out to longer wavelengths. And so that accounts for kind of the underlying shape of these spectra changing. And then the absorption lines change because of basically the atmospheres of these stars can support different elements. For an O star, its atmosphere is so hot, it basically breaks everything apart. It's just too hard to have a lot of molecules in those atmospheres. Whereas an M star is so cold, its atmosphere can have all sorts of molecules, and it gets this really complex absorption spectra because there's so many more things present in its atmosphere. Now, the last kind of spectra is an emission spectrum. So this is kind of the energetic twin of an absorption spectrum. So absorption spectrum are caused by absorbing light at given wavelengths from some continuum background radiation. But an emission spectrum is basically emitting light at those same wavelengths, but no continuum required because in this case, the spectrum is emissive, so it's actually emitting that light itself. Again, it comes back to those quantum interactions, and they have to have a given energy. And so that energy might be absorbing a photon to make a certain transition happen. But for an emission spectrum, it's the opposite. It's releasing a photon, and it has that given energy that's associated with this transition. So let's give an example. Probably the simplest example is a hydrogen atom. So this is one proton with one bound electron. So if that electron is in the lowest n equals 1 energy state for a hydrogen atom, it has about negative 13.6 electron volts of energy. If it's in the second level, it's at only negative 3.4 electron volts. So that's a difference between the two levels of 10.2 electron volts. Now, thanks to the handy relation between the energy of a photon and its wavelength, we know that a photon with 10.2 electron volts of energy has a wavelength of about 121.5 nanometers. So on the one hand, if you have a hydrogen with an electron in its lowest energy state, it might absorb a photon that has 121.5 nanometer wavelength. And this would then cause, a dip in the continuum. Alternatively, if you have a hydrogen atom where the electron is already in the second level, that electron might decay down to the first level, and then it would release a photon, and that photon would have the same energy that it took to excite it to the first place. So it would be 121.5 nanometers. And then that would be an emission line at that same wavelength. In fact, this particular transition is the first of what is called the Lyman series for hydrogen, and it is in the ultraviolet range of the spectrum. So just like absorption spectra are created by diffuse media, so too are emission spectra created by diffuse media. But in this case, the diffuse media is excited by some energy source that we probably can't see, and then it creates this emission nebula. This is because when light is absorbed in that absorption spectra, eventually whatever excited state it reaches decays, but that light now goes in any direction. You can see the emission spectra in places that you wouldn't see in absorption spectra. So one common example of emission spectra would be things like planetary nebulae. So these are kind of these nebulous clouds, and they have the energy source from that dying star, and so they can create these beautiful emission spectra. So these three different types of spectra can actually all be present in the spectrum of an object. So we already saw that how the sun and other stars spectra has both continuum and absorption spectra. But you can even have things that have all three. So for example, galactic spectra tend to, well, they're made of a lot of stars, so they have a lot of black body, continuum emission, and they also have absorption, again, from those stars and also from interstellar clouds of gas and dust. But they also have emission lines, again, because there are those excited clouds of gas and dust that are releasing all of this radiation at specific discrete wavelengths. Now, most stars are just continuum and absorption, but there are some kind of weird stars that have, in fact, emission lines as well. And this is something like a Wolf-Rayet star. So these stars are so hot and so massive that they basically create their own little shell of hot gas around them just because they're sending so much material into the space around them. And then that gas is so hot that it gets ionized by the star, and so then it creates emission spectra from the gas itself. So looking at the spectra of astronomical objects is a crucial part of astronomy. This is called spectroscopy, and it can give us so much information. The temperature, the composition, the distance, the redshift, the density. I'm probably missing more, but it's very, very important observational field of astronomy. So I mentioned that a rainbow is a spectrum, and a rainbow can be created from a prism or even just a droplet of water, right? In the sense of raindrops in a rainbow. So scientific instruments do something similar, but they just, kind of take it and refine it into a more precise and accurate process. It's usually using some sort of combination of prisms and grating to separate light out into its different wavelengths. A modern high-resolution spectrograph can reach a spectral resolution of up to 100,000. Now, spectral resolution is basically the wavelength of the light divided by the smallest difference between the light wavelength that you can see, so lambda over delta lambda. So if you have 100,000 spectral resolution for a given visible wavelength of light, say 500 nanometers, that means that you can tell apart light that's 0.005 nanometers apart in wavelength. It's very amazing. So hopefully you now understand a little bit more about what spectra are and how we use them in astronomy. I'm sorry if you're disappointed that we didn't get too much into the quantum interactions underlying these physical causes for the spectra, but hopefully now you understand what you're looking at if you see a spectral plot in a paper or if you are curious and want to look up information about spectra yourself. So thank you so much for joining me. I hope you enjoyed the letter S, and of course I hope you will come back and join us again for the letter T. All right, have a good one. Bye.